Unfortunately, so far, we've only looked at dynamical systems with 1, 2, or 3 dimensions in phase space. And the advantage of looking at low-dimensional systems like that is that we can actually visualize them. We can see all the variables in one plot. And that's, of course, very handy when trying to figure out what it's doing. In real systems, we often have very large numbers of particles or very large numbers of different kinds of dimension. And so our phase spaces can be huge, tens, hundreds, thousands. And if there's a large number of dynamical variables, even if it's something like 5 or 6, it's very hard to figure out what's going on by visualization. And a really good tool for dealing with those situations is the Poincare section. The idea here is very simple. You take a slice in 2 dimensions of your phase space. And then your actual trajectory will be flying around in phase space. And every now and then it will intersect at a point. And it'll keep on flying around in various dimensions. It'll keep on intersecting points. And so as it passes through, what you end up in your Poincare section is a series of points. Now if you happen to have a stable point, an attractor in fact, then ultimately this 3-dimensional or 200-dimensional path will end up stuck on that. Unless you happen to be directly on that 2D plane, you won't spot it. However, if your evolution is being attracted towards a single point, then it's very easy to figure out what's going on. You can see just by examining the vector of your phase space that the values are all becoming static. If something more interesting is happening, like it's turning into a loop, what would a loop look like? So a limit cycle, even if it's very complicated, eventually it could go through this several times, but eventually it has to meet up. And so what will happen is a limit cycle will have a finite fixed number of points that it just keeps going through again and again and again and again and again and again. And so if you're attracted to a limit cycle, it won't do that initially. So if you look at your section, you might have a few transient points where it gets away. Then after a while, they'll just start dotting backwards and forwards. 1, 2, 1, 2, 1, 2, 1, 2, like that. Or you might have 3 or 5 or 10, but a fixed number of points is a limit cycle. Now what about a chaotic system? A chaotic system will have a path that is so complicated, I'm not going to draw it here, but it's going to be very dense in a finite volume of space. In fact, it's going to be essentially infinitely dense because it's going to keep on passing and passing and not repeating itself. And so eventually, over a long time, you're going to have a large number of crossings of this Poincare section, and they're never going to repeat. So they're never going to start going through the same place again, but they're just going to keep on going denser and denser in a more baroque pattern. And when you get that and the pattern is getting denser and denser and denser over time, you've got a strong sign of a strange attractor. It's called a strange attractor because your dynamics is attracted to that. So if you start further away, you'll end up getting into the sort of the swirling levels. Think of the 2 lobes of the butterfly for the Lorentz equations. But because it's not a simple point or a simple limit cycle, it's a strange object. And so again, with imaginative names, we call it a strange attractor. Anyway, that's a good way of dealing with high-dimensional systems. You do a Poincare section.